Hello everyone, it's my pleasure to give a presentation at the American Control Conference. Today I will share our group research about the adaptive neural control for tilting quadcopter with finite time convergence. I will share the whole paper into the following 5 parts. First, let us review the unmanned aerial vehicles. We know the UAVs have a lot of advantages, such as high maneuverability, high concealment, and it can be used as sensor platforms with lower maintenance. And motivated by the above advantages, it can be utilized in a lot of applications, such as agriculture, photograph, or the transport vehicle. We know the quadcopter has seen a boost of popularity in the recently and generate great interest as a platform because it has a lot of advantages such as vertical taking off and landing, lower maintenance, hovering, and lower cost. But it has a lot of disadvantages. For example, the quadcopter we know it has only 4 impulses over the 6 degrees of freedoms. It means that the traditional quadcopter is an under-altitude vehicle, which means the poor maneuverability, reliability, and fault tolerance cannot be achieved. The generated force by the propeller only constrained in a single plane. Thus, this way couples the translational and rotational movements. Motivated by the above discussion, we would like to propose a novel fully altituded aerial vehicle, which can achieve more ability, such as developing the fully altituded flying vehicle. It's very important for operations in ruins or the narrow space. The performance of the conventional quadcopter is limited due to the generated force only in a single plane. Namely, this causes the translational and rotational movements constrained, and it cannot be controlled independently. Motivated by these requirements, several execution strategies have been developed to obtain fully controllability over 6 degrees of freedom. In this paper, we propose a novel tilting quadcopter consisting of 4 rigid parts: the body, servo, push, and the propeller as shown. The tilting angles can be indeed arbitrary to provide the desired force or torque in any directions. This suggests fully controllability in 6 degrees with more reliable and maneuverable abilities. Now, we will give the objective of this paper. We would like to address an adaptive neural control with faster finite time convergence for the proposed tilting quadcopter with parametric uncertainties. We propose this new novel concept, which suggests the translational and rotational movements can be controlled independently. Based on the Euler-Lagrange equations, we can develop its dynamics with uncertainties. To compensate these uncertainties, a novel adaptive scheme is incorporated in our adaptive neural control, where the estimation errors can be abstract and used as a neural term in the adaptive scheme. All the tracking errors and the estimating errors can converge to a small neighborhood around 0 in finite time. Moreover, the estimated width of neural networks can be guaranteed to converge to their optimal values simultaneously. First, let us develop our dynamics of the tilting quadcopter. According to the Euler-Lagrange equations, we will have the following dynamics equations, where in this system we know there have a lot of uncertainties such as the error damping coefficients or the moment inertias in this system. To compensate for the uncertainties in the system, we would like to develop the adaptive neural control with finite time convergence. However, we know a lot of works has been paid to guarantee the convergence of the tracking error. However, few results consider the estimated parameters. which means the estimated parameters before only stay around the preset value. The tracking errors and the estimated errors converge to a compact set rather than to zero. Few people consider the estimated parameter convergence, since the estimated parameters cannot be measured. Thus, in this paper, we not only consider the estimation convergence, but also the tracking error convergence. First, let us develop the estimation error-based adaptive neural control for the rotational subsystem of the tilting quadcopter. We define the ThA1 as the tracking error, and we can get the virtual control alpha1 as follows. We introduce an integral terms which can reduce the sensitivity to parametric uncertainties. Differentiating ThA1, we will have the dynamics of ThA1 as follows. Then, inspired by the backstepping ideas, we focus on designing the control inputs to drive ThA1 to converge. Then we will have the following equations. About the neural networks, we would like to rewrite the above equations as follows, where the dot f11 plus f12 equal to the tau plus f13. Applying neural networks to approximate the unknown dynamics functions, we will have the following equations. Then, by the mathematical method, we can establish a novel estimation error-based adaptive scheme in the right hand, where the ThA1 is a positive constant and W vector as the representation of WCI. Then we will have the oscillarity system state L1I as the following. According to the above discussion, we propose the following estimation error-based adaptive neural control. Then we will have the following theorem 1. Considering system with adaptive control and learning algorithm, if the matrix in system P is a positive definite matrix, it can be derived that the tracking error ThA1, ThA2, and the estimated error will converge to a small neighborhood around the origin in finite time. Moreover, the estimated weights converge to the region around their optimal values simultaneously. Let us share some simulation results of the adaptive neural control. From the following two pictures, we will see the rotational movements and the translational movements can converge to their desired trajectories in finite time. Then, the proof of the oscillarity vector L1 and L2 will converge to zero around the zero in finite time, which means the estimated weights of the neural networks can converge to their optimal values in finite time. Finally, we will give the conclusions of this paper. In this paper, we propose a novel concept of the tilting quadcopter, which suggests that the translational and rotational movements can be controlled independently. The complete dynamics is developed based on the Euler-Lagrange equations, where the parametric uncertainties contains. An estimation error-based adaptive neural control is further proposed to compensate for the uncertainties where the estimated weights error can be abstract from the auxiliary matrix. This indicates that not only the tracking errors, but also the estimated errors can converge to a small neighborhood around zero. Moreover, the estimated weights of neural networks can converge to their optimal values simultaneously. Finally, we give the simulation results to demonstrate the effectiveness of our proposed adaptive neural control. In our future work, we would like to extend our approach to the practical situations, such as considering the state constraints, external disturbance, and the fault-tolerant control. Thank you.